Hello, this is Dave Doyle and welcome to GeoLearn and the class today on fundamentals of geodesy and contemporary geometric datums, a transition from classical horizontal datums. So let's get started. Let's take a look at just the basic definition of a geometric datum versus our classical approach to what we've always referred to as a horizontal datum. In contemporary positioning, a geometric datum is three-dimensional. Classical horizontal datums were two-dimensional, latitude and longitude, or northing and easting, state plane coordinates, UTM coordinates. But a geometric datum is three-dimensional, latitude, longitude, and ellipsoid height. And the development of geometric datums has only really been capable with the development of space-based positioning systems such as the global positioning system. Now, in general, the approach to this is one of two ways. A practical datum, that is one that's the coordinates are collected using GPS or GNSS technology, and to the extent possible and practical, seldom change with time. Now, even though we know that everything is physically moving, all the tectonic plates are in fact in motion, we'd like to keep our coordinates as stable as possible for a practical sense, because the average day-to-day application of coordinates in the vast majority of the United States, of course parts of California, Washington, Oregon, Alaska, Hawaii are a bit different. They deal with some other issues. But for the vast majority of the United States, the North American tectonic plate is relatively stable. Not entirely, mind you, but relatively stable. So we can keep coordinates to a great extent fixed and stable over some period of time. Although one of the challenges that the National Geodetic Survey is constantly faced with is that increasingly the requirements from the various users community, which have traditionally been land surveyors, but now more so today, other groups coming in, other professions using high accuracy GPS and absolutely requiring just 1 or 2 or 3 centimeters in positional integrity. This is constantly an issue for NGS to keep the reference frame up to date. But at the same time, we can deliver a practical reference frame, one that suits the needs of the vast majority of surveying and mapping applications. We can also deliver what we might refer to as a scientific reference frame, and that is one, again, latitude, longitude, and ellipsoid height, just as we've seen here, but now with the added component of velocity. There are obviously many people in the scientific community, geophysicists and geologists and geodesists and others who don't care about keeping their coordinates stable. They want to know how much things are moving. The interesting part of technology today is that through one box, a GPS or GNSS continuously operating reference station, or a CORS, you can deliver easily both sets of coordinates to the user, so the user can decide what it is that they want to use. So contemporary geometric datums can be provided in one of two ways. Just a rehash of the relationship between our older datum, NAD 27 and NAD 83. We went from a system that was best fitting to just North America to one that is best fitting globally. Transition of the origin of our coordinates from a specific survey mark in the middle of a farmer's field in Kansas to Earth Geocenter. And of course, at Earth Geocenter, there is no survey mark.